Okay, so welcome again to another lecture, and in this class I will be talking about time dilations. And in the previous lecture we saw uh, some things about Lorentz transformation, and in this lecture we are going to talk about one of the consequences of the Lorentz transformation. So as of now we have transferred from Galilean transformation to Lorentz transformation. Sorry, this should be a T, Galilean transformation. And the result or the consequence of that is that light speed in vacuum is constant, or C is constant. And in natural units we have taken that to be 1, and for objects moving at velocities which are not light speed but somewhere below light speed, they will face some more consequences, and one of them is the time dilation. And I will be giving a brief introduction of time dilation in this video. Okay, so I am going to consider one clock observed by two different observers. So this is a clock, and this remains still with respect to some observer O, and the same clock is moving at a velocity v with respect to some other observer O prime. Okay. So now we will be seeing how time passes for them, and that will be different. Oh, this should be v vector. Okay. So for O, the proper time difference, this is nothing but dt square minus dx squared of the clock. As O sees the clock still, and O sees that the clock is in the same position as time evolves, so O doesn't see any dx, so this is 0 for O. So O sees this, and for O, d tau squared is exactly dt squared, or we can omit the squares. D tau is exactly equal to dt, and suppose between two ticks of the clock of the clock, that's delta t. Okay. But for O prime, let's see what happens. This looks like this. Okay. And if I take dt prime squared common, then I will get something like this, and this is exactly the velocity of the clock that O prime sees. So that should be v, right? So this is dt prime squared 1 minus v squared, or v vector squared. So d tau will be dt prime times 1 minus v squared to the power half. And as in the last lecture I have shown that the proper time is an invariant under Lorentz transformation, so d tau remains the same as O and O prime are connected through the Lorentz transformation. So this delta t will be exactly equal to this term. So here we get delta t equal to dt prime into 1 minus v squared to the power half, or dt prime is equal to delta t times 1 minus v squared to the power minus half. So, the observer O sees the time difference between two ticks of the clock is delta t, and O prime sees that the time difference between two ticks of the clock is dt prime, that is related to delta t with this expression. Okay. Yeah, so this is in brief time dilation, and this will be a short lecture. There is nothing else to tell here in an introductory talk about time dilation. And we can, I want to tell some more things about the apparent time dilation, or the Doppler effect caused by a moving clock. And that should not be confused with the relativistic time dilation. Okay, so I'm going to erase it. Suppose here is our observer, and here is a moving clock that's moving at a velocity v. This clock is a moving source of light, because information is coming to the observer with electromagnetic radiation or light at speed c. So, this clock, I can say, is a source of light that emits light at some frequency mu is equal to 1 over delta t. Then also the time difference between two successive emissions of light beams, or the time difference between two ticks, is given by this thing, as we have found earlier. However, during this time dt prime, the clock moves some more distance, and the second pulse of light needs to travel some more path to reach O. So, O will see the time difference between two successive emissions, or between two ticks. Not only this, but also there will be some Doppler effect added to this, because the second emission happens after some displacement. So, the first at first tick, a light emits from here and reaches O, and at the second tick the clock has reached at this position and emits the light, but it needs to travel this distance extra, and this distance is nothing but v dt prime, yeah, as dt prime is the time difference between two ticks. And for some reason I'm going to write VR, or radial distance. And Doppler effect can only be seen if there is some radial component of the velocity of the clock. Otherwise, there will be no Doppler effect added to the time dilation. So, between what O observes here, the time difference between when the second beam reaches and the first beam reaches will be, it will be dt prime, yes, if the clock was here, and there will be some more time added to this thing. So, some amount of Vr dt prime will be added. Remember, there is no dimensional defect here, as we are working in natural units. Here c is equal to 1, so Vr has no dimension here, it's just a number less than 1. So, taking dt prime common, we have 1 plus Vr, and that will be exactly equal to delta t times 1 minus Vr. This should be Vr. Okay, I think I should keep it v vector, right? Yeah. See here, this part is due to the time dilation, the relativistic effect, which depends upon the velocity of the clock, and this part depends on the radial velocity or the receding velocity of the clock from the observer, and this part is the Doppler effect. So, if light source is moving away, if it's moving away, then we will see a red shift. And why is it called red shift? Because if we find out the frequency, the V naught divided mu naught divided by mu will be exactly equal to 1 minus V square to the power half into 1 plus Vr to the power minus 1. This is because mu is inversely proportional to time. So, when Vr is greater than 0 or the clock is moving away from the observer, then we will see a red shift. See here, if Vr is greater than 0, that means we are dividing this term with some factor that is greater than 1. So, this term will be reduced, and this term here is less than 1. So, as V is less than 1, V square is also less than 1. So, 1 minus V square is also less than 1 to the power half is also less than 1, divided by some 1 plus some positive number will be also be less than 1, and that will show that V naught will be less than mu naught will be less than mu. So, the wavelength of this will be greater than this one. So, that's why it's called a redshift. Similarly, if it's moving transversely, if Vr is 0, then we will see pure time dilation. There will be no Doppler effects. Such a thing can happen when the clock is revolving around O. It has no receding velocity or approaching velocity, so there will be no Doppler effects. And when Vr is negative, that means that the clock is approaching the observer, then we will see a violet shift. Okay. Yeah, and if some observer is at this point and the clock is moving along this? So when the clock is here and moving along this, so the observer will see some violet shift here, and after the clock passes this line joining the trajectory of the clock and the observer perpendicularly, at this region the observer will see red shift. Okay, so yeah, if no receding velocity is there, then we will see purely time dilation, and if there is a receding velocity, then we will see time dilation mixed with Doppler effects. So yeah, that's all about time dilation for today, and we will be concluding this short lecture for now, and we will see you all at the next one.